Hi, in this tutorial we are going to learn how to get started with DE1-SoC board. At the beginning, we will configure the HPS using QSys and then implement the communication between HPS and FPGA. Next, we will run Linux Yocto on HPS and make it control LED through FPGA. Create new project and select your SoC device. Next, import the pin assignments. Note, all files I will use in this video are available on my Github. Now, let's add HPS to our design. Open QSys. Choose Processor and Peripherals, go to Hard Processor System and select Cyclone 5. Next, configure the HPS to suit your needs. Disable MPU standby and event signals. In this project, FPGA HPS SDM interface is not needed. Delete it by pressing minus button. That's enough for now. We will come back to the other configuration a bit later. In the System Content window, connect the main clock to H2F, F2H and H2F lightweight bridges. The HPS to FPGA bridge allows masters in HPS to communicate with slaves in the FPGA. Our goal is to make HPS read 10 switches and light up LEDs. Both peripherals are connected to the FPGA and the read and write operation will happen through H2F lightweight bridge. The lightweight HPS to FPGA bridge provides a lower performance interface to the FPGA fabric. This interface is useful for accessing the control and status registers of soft peripherals. In our case, peripherals are switches and LEDs. Also, export H2F reset output. Now add two parallel IOs, one for the LEDs and one for the switches. This PIO is for the LED. Set direction to output and width to 10 bits. Click Finish. Connect PIO's clock to the main clock, PIO's reset to the main reset. PIO Avalon slave must be connected to the H2F lightweight master. Add another PIO for the switches. PIO's external connections. It is also a good idea to name peripherals after its purpose. Now assign a unique base address for each peripherals. This base address is very important. Go to System, Assign Base Addresses. As you can see here, each PIO received unique base address at which it can be accessed through the H2F Lightweight Bridge Master. We will use these addresses later. Here you can add H2F and F2H reset requests, so you can, for example, reset HPS through FPGA, but we don't need it. Open Peripheral tab. In this tab, we add important peripherals to our HPS, such as Ethernet, SD card controller, USB and UART. The HPS clock tab should be left unchanged. Here is how it should look like in your project. Now let's configure the SD-RAM timing. If you are using different development board, your configuration will probably differ from mine. There are lots of values. You can download this QSys file from my GitHub. By the way, if you like this video, leave a comment about what you would like to see in my next tutorials. Also extract HPS IOs. Save and press finish. Next, we are going to add the HPS component in the FPGA design. Create new rich data file. In the pin planner, we see many HPS related nodes. All of them should be declared in our entity and eventually being connected to the HPS component. Add standard libraries. First, include connections for the LEDs, switches and clock. Now, list all HPS connections. That's a long list. I will just paste this part from my previous project. Next, we add the HPS component into our design. Go back to QSys and generate HDL. Next, select Generate HDR Example. Copy the component declaration and paste it into the architecture. Now, go back and copy the instantiation. And paste it. Next, we have to connect each HPS connection to its corresponding node, manually. Normally, a corresponding node has the same or similar name as the component signal, but sometimes there is a difference. Here, I made a mistake and assigned 1 to H2F reset, forgetting that this signal is actually an output from HPS. Later, I will assign it to an internal unused signal. If you don't have as much patience as me, you can copy this part from my video file. But from the pedagogical point of view, it's recommended to write this connection manually, at least for the first time. Finally, add the generated QSys file to the project. Before compilation, execute TCL script, run parameters and pin assignment files from your project folder. These files were generated by QSys. Now compile and wait. This will take a while. The second part of this tutorial is about writing a program for Linux Yocto, which runs on HPS. Run the embedded command shell from the Quartus installation folder, navigate to a project folder and execute generate file. This will generate an important header file, which we will need for the Linux software. If you are going to use my generate file, please don't forget to change the name of the project. New header file should appear in the folder. This header file contains all information about QSys components, in our case LEDs and switches. Next, we will write a similar program for Linux, which will read a status of switches and assign its value to LEDs. Remember, the interaction between the HPS and the FPGA goes through the lightweight H2F bridge. In the datasheet, we can find the base address of the H2F lightweight bridge. Also, H2F lightweight address region is 2 MB long. Let's define these parameters in our program. Because we want to read and write values directly from the memory addresses, we define some pointers. The next command opens the system memory. The map command creates a new mapping in the virtual address space of the process. The size of the space corresponds to the H2F address region. The address of the new mapping is returned as virtual base pointer. To access switches or LEDs, we add the base offset of the corresponding PIO. Remember, this offset is set in QSys and is now defined in our HPS header file. We are almost done. Let's read a value from a switch register and assign it to LEDs. Because we defined our pointers as void at the beginning, we should cast an assigned integer on it now. By doing so, the program will interpret the value stored at the pointed memory address as unsigned 32-bit long integer. I also add 1 second delay between read and write operation. After the delay, the program should print out the value of the switches as a decimal number. We will see this value in the command window later. That's it. Save the file, rename it as main.c. For compilation, you will need makefile. You can just take mine or make your own. The name of the output file is defined in target. Start embedded command shell, navigate to your project folder and type make. Next, load your project into the FPGA. In case you are also using DE1-SoC board, you should add SoC HPS device. Make sure SoC HPS appears before the FPGA. If it's not, move it up. Insert the SD card with Linux console in it. You can download one from the official Terasic page. Start party, you should see Linux loading. After Linux is loaded, log in using root. Next, we need to establish Ethernet communication between your PC and DE1-SoC board. I am using crossover cable to connect DE1-SoC directly to my laptop. Next, assign an IP address to your board using ifconfig ATH0 command. Finally, go back to embedded command shell and transfer the compiled file to DE1-SoC using scp command. Next, use command chmod +x to make this file executable.